Hi, welcome to my talk on balanced donor coordination, which was given at EC'23. My name is Matthias and this is joint work with my supervisor Felix Brandt, Erel Segal-Halevi, and Warut Suksompong. Every year, billions of dollars are donated to charity, either privately or via some donation program. Two examples for such donation programs are Dzięki per Mille and employee charity matching programs. Dzięki per Mille is a program run by the Italian Revenue Agency, which allows Italian citizens to contribute 0.5% of their personal income tax to one of over 71,000 organizations. In that way, more than 510 million euros were raised in 2022. Some huge companies like Microsoft or Apple run so-called employee charity matching programs, where they double the amount of money that their employees contribute to charity. What most of these donation programs have in common is that a donor can select only one organization and acts completely on her own, meaning that she's not aware of the donations of others. That's why we think there's a huge potential to increase the donor satisfaction by, first of all, taking into account finer preferences over the organizations, so allowing donors to not only report the one charity they want to contribute to, but maybe a set of charities they approve, or even report valuations for different charities. Secondly, we think the donor satisfaction can be hugely increased by coordinating the donations. What do I mean by that? Let's look at an example. Assume we're given 3 charities, one that provides shelter, one that protects nature, and one that provides healthcare. We are also given 4 agents who are willing to contribute a certain amount of money. The arrows here now indicate how much an agent likes a charity. So the blue agent really supports shelter. Nature is still important to her, but she does not care about healthcare at all. So if agents do not coordinate, I think we can assume that every agent would donate to the charity they like most. So the green agent will donate to nature, same for the yellow agent and the red agent. Only the blue agent will donate to shelter because he likes that charity most. Summing up the donations, we see that healthcare does not receive any money at all, although it is approved by the yellow agent and the red agent. This is clearly not what the donors intended, and presumably these 2 agents are willing to partially transfer part of their donation to nature, to healthcare, such that healthcare also receives at least some money. Let's formalize these observations. So we're given a set N of agents with individual contributions CI. The agents are able to donate these contributions to charities from a set A. In our examples, these were the charities shelter, nature, and healthcare. A distribution delta now states how much money every project receives. So clearly, the total amount of money all charities receive need to sum up to the total amount of contributions of all agents. Each agent now has a valuation for every charity X, named VIX. and we assume that they have Leontief utility functions. So their utility for a certain distribution delta is given by the minimum fraction of distribution divided by the valuation for the specific project, where we only take into account charities which are valued strictly positive by agent I. So as you can see, the larger valuation VIX, the more important it becomes for agent I that charity X receives a lot of money. In the case that all valuations are either 0 or 1 for all agents and charities, we speak of binary Leontief utilities. A distribution rule F now returns a distribution delta for any profile where a profile consists of all valuations and the individual contributions for each agent. Before asking ourselves what might be a good distribution rule for our setting, let's have a look at some related literature. So far, only the linear utility model has been considered in the literature. So staying with the example where agents approve a certain set of projects, they are indifferent how money is distributed on the projects they approve. So their utility just equals the total amount of money that's on approved charities. Another difference to our model is that mostly exogenous fixed endowments are considered. So the money that is money or time or probability that is distributed is not initially owned by the agents. Secondly, a problem that seems to be a little bit related to ours is that of the private provision of public goods, where agents distribute their wealth between a private and a public good. However, the problem there is that agents need to decide, well, who will contribute to the public good and who can keep the money for themselves, which is not the case in our setting, because here agents already have some amount of money they are willing to contribute to a public good, in our case, charities. Lastly, a very hot recent topic is participatory budgeting, where again, we have an exogenous endowment, but in this case, also fixed costs for projects. So projects are either fully funded or not funded at all. Note that in our setting, there is no such cap for the charities. So you can donate or allocate any amount of money to a charity. Returning to our example from the beginning, we can now see why the yellow and the red agent are particularly unhappy when considering Leontief utilities. Therefore, we translate this picture into a table where you can see in this column the contributions of each agent, and their valuations are indicated by these colors here, where this dark gray means valuation 2, so agent 2 values nature with 2. The light gray indicates valuation 1, and white indicates valuation 0. As we can see here, both agents 2 and 4 receive utility 0, because one project they value positively, namely 1, receives 0 contribution. So the minimal fraction is 0 here. So they both get utility 0. So indeed, they have an incentive to move part of that contribution to healthcare. So let's look at this distribution, where now agent 4 moved her contribution to healthcare, while agent 2 moved her contribution from nature to shelter and healthcare. So we can see agent 2 and agent 4 now both receive utility 1.5. In fact, you can see here that no agent is able to increase her utility by redistributing her contribution. So for example, looking at agent 3, as soon as she moves some contribution from shelter to nature, her utility will decrease from 0.75, which was her utility when her Leontief utility, when we divided 1.5 by her valuation for that project, namely 2. So as soon as she moves some amount of money from shelter, the total amount will decrease, and with that also her utility. A distribution which can be decomposed into individual distributions such that no agent has an incentive to deviate, we call an equilibrium distribution. And in fact, what one can show is that each profile admits a unique equilibrium distribution. So we can define a rule that always returns the equilibrium distribution, which we call equilibrium distribution rule, or short EDR. So now that we have a candidate for a good distribution rule, we of course need to investigate what properties are satisfied by that rule. To start with, what one can show is that the distribution returned by EDR maximizes Nash welfare, so the product over the agent's utilities. And therefore it is Pareto efficient, meaning that there does not exist any other distribution where no agent is worse off and at least one agent is strictly better off. A second very important property is strategy proofness, because we want agents to report their valuations truthfully, to aggregate them properly. So they should not have an incentive to misreport their valuations. In fact, our rule satisfies an even stronger axiom, namely group strategy proofness, which tells us that even a group of agents can collectively misreport their preferences in a way such that no agent gets worse and one agent at least gets strictly better. Looking at an example where agent 2 and agent 4 misreported their valuations for healthcare, so increased them from 1 to 2, we see that the distribution changes in a way that leaves both agents worse off under their truthful preferences over here. Another very important axiom is that of participation, right? Because we want agents to donate to charity. We want agents to donate to charity as much as they can. So we somehow need to ensure that agents are really strictly better off by increasing their contributions, and not that and that their contributions are allocated to aren't allocated to projects, to charities which they do not like at all. And indeed, this is the case for EDR. For an example, let's look at agent 3, who increased her contribution from 1 to 2. And under the new distribution, we see that her utility increased from 0.75 to 1. Another property EDR satisfies is that of preference monotonicity, which means that if an agent increases her valuation for charity X, this can only increase the total amount of contribution charity X receives. So in a way, the preferences of the agents are really reflected in the contributions that are allocated to the charities. Finally, EDR also satisfies contribution monotonicity, meaning that if an agent increases her contribution, no charity can receive less than before. So in this example here, again, agent 2 increased her contribution from 1 to 2, and we see that every total contribution to the charities here is in this case even strictly larger than before, when agent 3 only contributed 1. Finally, one can ask, well, EDR seems to be a very good rule, but can it be computed efficiently? And indeed, this is the case. EDR can be computed via convex programming, which just follows from the fact that it maximizes net welfare here. Let me conclude with some further remarks and future work. So apart from all the axioms EDR satisfies, there also exists a best response dynamics converging to EDR. With best response dynamics, I mean a dynamics where the agents distribute their contribution in a certain way, then observe the total overall contributions to the projects, and based on that are allowed to reallocate their own contribution. And what one can show is that indeed this process will converge to the equilibrium distribution, showing that it's very natural also from a behavioral perspective. Secondly, when we restrict ourselves to binary Leontief utilities, so agents only report valuation 0 or 1 for charities, one can show that EDR can be computed not only via convex programming, but via linear programming. Secondly, then there exist also some very interesting connections to maximizing egalitarian welfare for both the agents and the charities. Finally, one has to mention that our results do not carry over to other utility models, for example, concave utilities as Douglas. Nevertheless, it is worth investigating such models regarding equilibrium distributions and other axioms, so which axioms can be satisfied at the same time in these other models. Secondly, another very interesting question is, well, can we characterize EDR via some attractive axiomatic properties? And finally, And maybe most importantly, we aim at increasing the impact of existing donation programs by implementing EDR and coordinating donations. Thanks for your attention.